Say something. Hello, can you hear me? Hello?
There are people online.
I think they can hear you.
Okay.
Yes, that was Guru said. Yes. Okay, so continuing this afternoon, we've got some short talks. That means they are 20 or 15-minute talks with 5 or 10 minutes of discussion, and then 5 minutes to switch over. And as our first speaker, we've got Hongzheng Zhao, who is from the Max Planck Institute of Complex System. And he's going to tell us about orthogonal quantum many-body scars. Thank you very much, Hongzheng.
Thanks a lot for the introduction. And I'm Hongzheng from MPIKS. Today, I'm going to talk about our recent work on orthogonal quantum many-body scars. So let me first briefly start from what we are interested in. So we're actually interested in analyzing a many-body system, and especially how do this many-body system equilibrate. And we know that for classical many-body systems, and because we normally have a ergodic dynamics, and after sufficient long times, whenever you have a large degrees of freedom, they will actually eventually equilibrate to some steady state. But and also actually this equilibrium steady state can be captured by a few thermodynamic quantities. However, nowadays we want to understand how does quantum many-body system equilibrate or thermalize. But indeed, this is not a very straightforward generalization, simply because if we consider a closed quantum many-body system, and because of the Schrödinger equation is indeed a linear equation, and you can't, if you start from a pure state, and you will always remain pure, and you can never reach a thermal ensemble, let's say. However, there are many numerical and experimental evidences showing that indeed, although your system cannot thermalize globally, but indeed your local observables can indeed be predicted by thermal ensembles. And then during the past 2 or 3 decades, and people trying to figure out why it happens, and now an intuitive answer to explain such a phenomena is that whenever we look at a sublocal region of our many-body system, indeed the rest of the system can play as a thermal bath, and then it actually can heat up the system locally. And there are actually a more a rigorous way to describe such a phenomena. It's actually so-called eigenstate thermalization hypothesis. So it basically says that such a thermalization behavior actually can happen at each eigenstate level, apart from the very low energy, for instance, the ground state. But most of this, okay, so if we compute the expectation value for of the local observables for each eigenstate, actually we will notice that such a we will actually get a smooth function versus the eigenstate energy, and they can basically be obtained by using the macrocanonical prediction. And also, because the system thermalizes, we will normally expect a volume law scaling of entanglement entropy. So normally it basically means that the system thermalizes, and you can establish correlations between any parts of the system. And so this is just an example showing that after a quench, I mean, people first prepare their ultra-cold atoms in the left part of their optical lattice, and then they quench the system. And after sufficient long time, you'll notice that all of the dynamics is ergodic, and all of the particles actually uniformly occupy your optical lattice. So this is also indicate that the final state we actually lose the memory of our initial state, and it also indicates that thermalization happens. Well, then there is a very important question is, how can we break the ergodicity of the dynamics, or is it possible to avoid thermalization to happen? And there is a very interesting method for this purpose, which is called the many-body localization. It begins from Philip Anderson So the basic idea is that if you put sufficiently strong randomness into your lattice potential, you can basically localize your particles, and then these particles can't really talk to each other if they are far away from each other, and then you can basically break the ergodicity. And then if you again to study the expectation values of any local observable and plot it versus the eigenenergy, and instead of having a continuous function versus energy, but instead you will just get a very chaotic behavior in this in the distribution. And there's another the direct consequence in the experiment is basically, again, you can prepare your initial state in the left part. And then so people just impose many disorders in the lattice potential, and even after sufficient long time, actually the system can still maintain the memory of the initial state for a long time. Very recently, I think it's so like 5 years ago, people noticed that there is indeed some other ways that which can also breaks the ergodicity of the dynamics, which is recently been named as quantum many-body scarce. So basically, they first do an experiment in the Rydberg atom setup, and then they notice that whenever they will show a very slow or even no thermalization process in this domain wall density of this of their Rydberg configuration, only for very special initial state. But if you choose some other more generic initial state, you will actually see a very fast thermalization as in the other non-ergodic systems. So to understand such a behavior, people actually notice that, okay, there are some very special eigenstates in a many-body spectrum. They are later called quantum many-body scarce. And so this very special eigenstates, they have relatively low entanglement entropy. Normally they exhibit subvolume law entanglement, and these states actually break the eigenstate thermalization hypothesis. And then if your initial state have a large overlap with the special scarred eigenstates, you can expect some very slow thermalization process. And over the past few years, I mean, people notice that there are many different ways which can lead to the existence of many-body scarce. But for our purpose, the most relevant ones would just be the so-called Hilbert space fragmentation. So the idea is also very simple. We know that whenever we have some special symmetries of the system, we can block diagonalize our Hamiltonian, right? And then if we prepare an initial state in a given symmetry sector, it's impossible for you to escape from that given symmetry sector. But however, due to some special reasons, for instance, some additional conservation law, for instance, of dipole moment, or due to some kinetic constraints of your Hamiltonian, you can actually have additional fragmented structure even you fully resolve the symmetry of your system. And if the fragmented subspace is sufficiently small and you don't have enough number of states to thermalize your system, and you will normally just expect some very slow thermalizing behavior, or even no thermalization, or some coherent oscillations. Just to give a very simple example to show in which case you can have this Hilbert space fragmentation. So here I just consider a fermionic model, which so your particle can basically hop in the nearest neighbor, but in order for such a hopping process happen, you must guarantee that you have non-zero occupation numbers on your neighboring sites. So such a behavior can be called like a density-dependent hopping process, which can be realized by using, for instance, Flockade engineering. And if we consider a very simple initial state, so just as shown here, which involves six sites at half filling, and you simply apply this Hamiltonian onto such an initial state, and you notice that only the particle in the central two sites can move, and they can hop back and forth, but the other four sites on the boundary, they are actually frozen due to this kinetic constraint. And it's not only a finite size effect, but you can indeed argue that it also happened for infinite large system size at a finite fermionic filling. So the idea is also simple. You basically treat these 6 sites as a building block, and then you make a product of them. And simply because you can't really hop or move particles between different building blocks, you basically you simply cannot thermalize your system, and all of the coherent oscillations will only happen within each building block. And there is another important feature which comes from this entanglement entropy. So simply because there is no correlation between different building blocks, you can, depending on your cut, you maximally can get area law entanglement entropy. So after you quench such an initial state, this is not only a very special feature for such a very special model, but indeed in many previously identified quantum many-body scarred models, they also show sub-extensive scaling of entanglement entropy. And just by studying the scaling law of the entanglement entropy, I mean, this has also been recognized as a way to identify your quantum many-body scars in a overall thermal many-body spectrum. Yes. Yes, in this case, in each building, in each small building block, it's just effectively a 2-level system. Yeah. Yes. Yes. So in this way, if the effective dimension for this special initial state is only 2. It's very simple. But overall, if you don't have this kinetic constraint, you actually can have a much larger Hilbert space. In this case, it's even simpler than free fermion, right? It's just a 2-level system. But you also have, you also have other fragments which shows non-integrable spectrum. It actually depends on how many filling that you have for this fermions. You actually, the total Hilbert space can be fragmented into either fully integrable and also actually non-integrable sectors. It depends on your initial state. So that's why we call it not a very generic way to break integrability, but to break ergodicity of your dynamics. But it really depends on your initial state. Yeah. So here in this project, so what the main question that we want to address is, can we have quantum many-body scars, but with volume law entanglement entropy? Or from a dynamical point of view, can you have a coherent oscillation? For instance, it just never decay, but still, if you check the entanglement entropy scaling, you have volume law. So the intuitive answer is no, simply because within the ETH paradigm, normally the volume law scaling of entanglement entropy goes hand in hand with relaxation of local observables. But and also in all of these previously identified quantum many-body scars, they normally have sub-volume law entanglement scaling. But here we will show you that it is certainly possible. And basically, what we want to do is we will use a multi-component system where they have interspecies interactions, and these special interactions can actually break the eigenstate thermalization hypothesis in an interesting way. And the one very interesting example is a so-called quantum disentangled liquid. So this type of states is proposed like 7 or 8 years ago. And the basic idea is you have a strongly correlated system, but some of the degrees of freedom follows area law scaling of entanglement entropy, where the others have volume law entanglement entropy. So recently, there are also many research proposing different models to realize such a special state, but none of them really can answer our question because they don't really show persistent oscillations. So here, what we want to do is basically to introduce a model hosting quantum many-body scars in these quantum disentangled liquids. To achieve this, we will construct a model which I will call this orthogonal metal with additional kinetic constraints. But just before I show you the full model, let me first introduce what do I mean by this orthogonal metal. So it was proposed in 2012. And the basic idea is they just write down a toy model to show this, to show the existence of orthogonal metal. And the idea is you have two different physical degrees of freedom. So so you have fermions which can hop on the sides, but you also have spins living on the bound. And whenever the spin degrees of freedom can interact in the x direction, and but the interaction rate will depend on the fermionic occupation. But when also in a similar way, I mean, the particle, whenever it wants to hop, it also depends on the polarization of the spin in the middle. For this model, we can actually perform a duality plus some local transformation, and then indeed the system hosts two emergent degrees of freedom, which are decoupled. So one is a emergent spin degrees of freedom, which can be described by a simple transverse field Ising model, where the other emergent fermionic degrees of freedom it can be simply captured by a free fermion hopping on a 1D lattice. So in this case, we can also show that the correlation function of these physical degrees of freedom are simply products of this both emergent degrees of freedom. And there is a very interesting situation where you don't really have any correlation in these spins, in these tau spins. And in this case, you can actually have zero correlation function for your physical fermions, even though your emergent fermions can have non-zero correlation function. So in this case, people actually say, okay, there's two types of fermionic degrees of freedom are actually orthogonal to each other. So that's why people also call it as an orthogonal metal. But what we do is we simply introduce additional kinetic constraints to this original proposal about the orthogonal metal. So what we do is simply, you see that we gave additional density dependence to this fermionic hopping process. But by introducing this additional density dependence, we don't, so the separability of these different emergent degrees of freedom still holds. But the only difference will appear here. So basically the fermion, instead of being a free fermion, and now you also have this density dependence. Therefore, you have kinetically constrained fermionic dynamics. Therefore, you also have Hilbert space fragmentation and also many-body stars. And also you can exhibit coherent persistent oscillations. However, for the spins, we also introduce this additional integrability breaking term. Therefore, such a system of such a emergent spins actually follows ETH prediction and can also generate a volume law entanglement scaling. But we know that if we look at all of these correlation functions for our physical degrees of freedom, they also exhibit coherent oscillations just because our emergent fermion shows these oscillations. And this is just a numerical verification showing that whenever we measure the correlation function for fermion or correlation function in spins, they all, most of them will show some oscillatory behavior, but also some in some other correlation function they actually saturates. But the interesting bit is because we have we have emergent spin degrees freedom, which can generate this extensive entanglement entropy, and therefore in this case, when we study the entanglement scaling over this physical degrees of freedom, we also have rapid entanglement growth, and it will saturate at a plateau. And if you look at the average plateau value, they actually scales as a volume law scaling of the entropy. But we also know that for this emergent fermions, they are kinetically constrained and they only show area law entanglement. Therefore, such a model will host the quantum disentangled liquid. But on top of that, we now have persistent coherent oscillations in correlation functions or local observables. We can also understand why we break ETH from the eigenstate point of view. So basically here we plot the overlap between the initial state and most of this eigenstates. And we actually see that we actually overlap with a large number of eigenstates. But the point is, if you look at a single eigenstate, they're different. There are actually two eigenstates there which are paired together because we have two separated emergent degrees of freedom, and their energy separation is 2T, which corresponds to the kinetic energy for this emergent fermions. So in this way, such a separability actually breaks ETH. But if you check the entanglement entropy for the eigenstates, unlike the previously identified quantum many-body scars, but here they rather have a relatively large entanglement entropy for the eigenstates. And now we can also ask what will happen if we weakly break this separability of the system, and we will lose the pairing mechanism in the spectrum, and you don't really see the paired eigenstates anymore, and also the eigenstates will not persist forever, but rather have a finite lifetime. And now the lifetime of this oscillation actually, as we verified, it follows the Fermi's golden rule type of prediction. So as a brief summary, so basically we come up with a model which actually enlightened from this orthogonal metal, but which hosts two different types of degrees of emergent degrees of freedom. And for one of this, it's actually a thermal spin chain, but for the other, it hosts quantum many-body scars. And in this case, if we look at the physical degrees of freedom, we actually can have coherent persistent oscillations, but also with volume law scaling entanglement entropy. And in this year, there are also some other works. They also show that in other models, you can also have many-body scars with volume law scaling. And there are also open questions in this direction. For instance, once we break this separability of this model, how can we stabilize our quantum many-body scars by using some, I don't know, this is an open question. I mean, how can we basically stabilize all of this damping coherent oscillations? And there are also other questions. For instance, there are many different multi-components many-body system, and can we also impose some kinetic constraint, but induce some other types of non-ergodic dynamics? For instance, in many lattice gauge models, you can say, okay, if I only introduce kinetic constraints to my fermionic matter, can I also introduce non-ergodic dynamics to my gauge degrees of freedom? And in the end, I would like to thanks for your listening. And if you want to check for more information, you can just look at our previous two publications. And also, I would like to thank my collaborators, Joseph Vavash, Adam Smith, and also my two supervisors, Florian Mentert and Johannes Kmello. Thanks a lot.
Okay, we're open to questions.
Yeah.
So is it right that you need a special initial state
Yes.
for this to happen? So are there any systems where you don't need a special initial state and each state will maintain coherent oscillations?
Well, that's pretty like a purely integrable model, right? If for whatever initial state, you can say, okay, a collection of two-level system, and it does, if they don't couple, you always have coherent oscillations, right? But in this case, it's more like an integrable system. But here we would like to say, okay, is it possible to show such a behavior when we have, relatively non-integrable and strongly interacting systems?
Okay, I can ask a question. Have you any thought about how we could test this in an experimental system?
It's very challenging, I would say. So first of all, I mean, the kinetic constraints, we do have proposal how to engineer them by using periodical driving. But then this is also like very difficult in experiment because you have Flockade heating and you need to consider how to suppress them. Another thing is we do have this, let's say, three-body interactions between both spins and also fermions. So perhaps we can, but this to engineer such a three-body interaction, you can indeed use in this code atom platforms. And there are many ways that people figured it out that you can just also fine tune your state and then to mimic, for instance, lattice gauge models. So there are many ways to do this, and then perhaps they can also, use these two boxes for lattice gauge theory, and then they can additionally they use flow-gauge driving to engineer this kinetic constraints. But I mean, I have to say this is still relatively difficult. There are too many different techniques that you need to do, and it seems it's not really a simple task, even directly tested in solid state system, because there it's really hard to study non-equilibrium physics, and also it's hard to measure any entanglement entropy, such a quantity like this. But in nowadays ultra cold atoms platform, you can indeed measure, for instance, second order Rayleigh entropy just by measuring some local observables. That's actually already doable.
Well, let me make a follow-up question.
Yep.
Anderson, in proposing the predecessor of these ideas of antibody optimization, was motivated by experiment. What experiments motivate your work?
I think it's actually there are many
observations.
Okay, so basically the community that study quantum many-body stars is a big motivation, and there are so many proposals showing different types of stars, and they all believe that the subvolume law entanglement scaling is a reason that why you see slow thermalization process. But here we feel this is actually a wrong, or at least the incomplete thoughts, because the scaling of the entanglement entropy is not the whole story, but also the prefactor for your entanglement scaling is also very important. Because here, as in our model, we only entangle the states in half of the degrees of freedom. So we want to somehow to construct a theoretical model to show that, okay, there are some other possibilities to break the ergodicity of the dynamics.
I guess you began with a very nice introduction with taking a large quantum system and looking locally at it and saying, is there a situation in which this local part of the system does not equilibrate? That was part of the motivation.
Yeah.
But clearly, from a classical mechanics is obviously, we believe, a limit of quantum mechanics. And we know, look at that light, look at engines, that when you pump energy into a system, you can keep it running out of equilibrium as long as you keep pumping the energy in. In fact, your brain is another example. Okay, so isn't that a proof of principle to begin with, or is that different to what you're
there is a crucial difference, which so here we basically consider a closed quantum system. There is no energy.
But at the beginning, you talked of a huge quantum system with a local region, right?
Yes.
Well,
but
an engine is a subpart of a huge quantum system that is receiving energy from the battery, for example. Right? And clearly, as long as the battery provides energy, it keeps operating in its non-equilibrium mode, right? But so that was your original. I'm giving that as an example of your original motivation.
Okay, sure.
That stays out of equilibrium. Why is that not what you're interested in?
Okay, so let's say if you have a battery, there will be a day that you run out of your energy.
Yes.
After sufficient long time, your system will equilibrate.
Well, if it's the sun, it takes a long time.
It takes a long time, but let's say we consider infinite long time. You do have a time that you run out of anything, right? So we want to say whether such a behavior always happen, or does everything always thermalize, or they are exceptions which don't thermalize. And there are many different ways to do this. And here we just provide another example showing that it can avoid thermalization, and also you have interesting entanglement entropy scaling behavior.
What you mean by that is that in some thermodynamic limit of the small system, the time scale will become exponentially large. Is that what you mean?
No, that's actually not the case. I mean, for many-body system, for quantum many-body system, the actually thermalization can happen very quickly. I'm just saying that
a state that's put into a scar state.
The
claim is that time scale becomes very long. It doesn't equilibrate, in fact, right?
It still equilibrate. It really depends whether you have a perfect scar which are completely decoupled from all of the other thermal eigenstates, or you have a weak coupling there. So here I actually show the damping process, which basically I introduce a very tiny coupling between my perfect scars and other thermal eigenstates. And you see that following Fermi's boundary rule calculation, you do see a finite decaying rate. And such a decaying rate doesn't really depend on your system size. It actually converges in system size. So, but still you have a controllable way to understand how do you lose the scars and what will happen if you have perfect scars. Yeah.
One question. So, I mean, you're talking a lot about these decoupled eigenstates. You have a nice picture of a block diagonal Hamiltonian.
Yes.
Now, the textbook way of getting that is through a symmetry.
Yes.
Block diagonalization.
Yes.
Here, I don't think you have a symmetry, at least not an obvious one.
Right.
So, is there something that's creating these in a generic system, or does it have to be a finely tuned, specially constructed system to see this?
This is a very, very interesting question because, okay, so there are different ways to lead to this quantum many-body scars. So one reason is from symmetry. So they actually study this quantum many-body system preserving, for instance, dipole moments. And there, even if you fully resolve your dipole conservation, you can still have furthermore fragmented subspace. That's one way. That also leads to this, for instance, very small subspace. But here, that's correct. I don't really have a symmetry reason for this to happen. And it happens because of the additional kinetic constraints. That's not really directly related to symmetries.
So if you are close to an integrable point, let's say, and you approach this integrable point, or is there some understanding if there is a proliferation of scar states, or if the density of scars increases and eventually everything is non-thermalizing?
I think the interesting bit about this quantum many-body scars is that they don't really come from an integrable limit. So you can certainly ask, like, okay, we start from an integrable limit, and what is the time scale that we lose the integrability of my system from a dynamical point of view? That's one way to study, but for most of this, and in there, I think you don't really have this strong dependence on initial states.
So you say if you have a scar state, it doesn't mean that it's non-thermalizing, it's just very slow thermalization.
So it depends. It depends. So if in one case, it's that you have perfect scars, so it's completely decoupled from anything else. And in this case, you never thermalize. But it really depends on your initial state, because it only happens for very special initial state. And if you pick some other initial state, you can thermalize very quickly.
I see.
Yeah.
And is there any hope that if you take the cold atom experiments, let's say relatively small systems, and you can prepare lots of different initial states, that you can map this out more systematically?
Okay, they are already
for the case where you saw that there is still memory. I mean, how long did they wait? A year or a few days? Or?
No, actually, so there are actually two questions. First is, can you also verify quantum many-body scars with ultra cold atoms experiments? And the answer is yes. So they are already, experimental groups from Munich. They try to simulate it actually originates from Stark many-body localization, and they have a huge tilt in their optical lattice. And in the tilt, if the tilt go to the infinity, they actually can produce this Hilbert space fragmentation, and they can actually run very long time dynamics. For instance, up to TJ around 100 or even 1,000. They can see a very pronounced oscillation if they choose proper initial states. That's one example. So the second is, in the very beginning, I showed some pictures to showing some memory of an initial state that you don't really need to wait for decades. So the point is, you only need to see, you have a clear time scale where your system thermalizes. It normally happens at a TJ around 1, for instance. It happens very quickly. And if you have sufficiently strong disorders, you see that clearly beyond this thermalization timescale, your system still keep your memory of the initial state. You don't really need to wait for it's impossible in experiment to verify for arbitrarily long timescale. But as long as you can separate these two timescales, you can say, okay, you have a localized system and you keep your initial memory.
Okay, thanks. It's a great talk.
And so.
I have it running. Let me see if I can share.
Yeah, the screen is showing up now, which is good.
Okay.